Hello there, and welcome to our quiet journey tonight. We are drifting into the magnificent realm of solar systems, where worlds stranger than you can imagine exist in a cosmic dance of time and gravity. Our own solar system is only one story in a vast library of celestial arrangements. Each star surrounded by its own family of planets, moons, rings, and mysteries. Out there in the silent dark are systems of twin suns, molten planets, and worlds floating free in the endless cosmos. This is not just a journey through space. It is a journey through wonder into the hidden architecture of the universe. The things we will discover are not only strange, but beautifully real. These faraway systems might challenge what we think life needs, or what a planet even is. So, before you get comfortable, take a moment to like the video and subscribe. Let me know in the comments where you are in the world and what time it is for you. Let's begin. Some solar systems have planets orbiting two stars. Imagine, if you will, the profound spectacle of sunsets arriving in pairs, a double descent of light painting the sky with an extraordinary palette of hues, unlike anything we experience on Earth. On such worlds, the very rhythm of day and night, the fundamental pulse of existence, is dictated by a celestial duet, with tides pulled by the complex, interwoven gravitational forces of not one, but two suns. These are known as circumbinary systems, where a planet doesn't just loop around a single star, but instead threads an intricate path around both stellar partners at once. This orbital choreography, seen from the silent dark of space, looks less like a simple, predictable ellipse, and more like a braided ribbon, an elegant cosmic dance woven through shifting fields of gravity. The very possibility of stability in such a complex arrangement might seem counterintuitive. One would imagine the constant pull and push from two competing gravitational giants would tear any nascent world apart. Yet, stability is indeed possible. It's achieved because gravity, while profoundly complex in these scenarios, can settle into repeating rhythms. This occurs when the distances between the stars, their individual masses, and the planet's own mass and orbital distance fall within certain precise, harmonious ranges. These celestial bodies find a way to balance each other, moving in a grand, predictable waltz that allows for the prolonged existence of a planetary companion. The skies on such a world would be a canvas of perpetual change. The brightness would wax and wane, not just with the planet's rotation, but as the stellar partners eclipse each other or drift apart from the planet's unique perspective. Imagine seasons unlike anything known on Earth, not merely defined by axial tilt or distance from a single sun, but by the ever-shifting interplay of two radiant bodies. One star might be a brilliant, golden orb, while its companion could be a cooler, dimmer red dwarf, casting long, crimson shadows as it weaves its way across the firmament. The light would shift from intense, dual illumination to a softer, singular glow, creating a dynamic, ever-changing environment. Studies into the formation of these exotic worlds suggest that dust and ice, the fundamental building blocks of planets, can still gather and coalesce, even amidst the turbulent push and pull of a binary dance. While the process might be more challenging, and growth may pause and resume in fits, and starts as spiral waves sweep through the protoplanetary disk, matter finds a way. It demonstrates nature's incredible flexibility, its persistent ability to find a pocket of order, a stable eddy in the cosmic maelstrom, where matter can congeal and slowly, patiently build a world. The existence of these worlds profoundly widens the stage for potential climates, atmospheres, and perhaps, someday, even the intricate chemistry of life itself. They are a testament to the universe's boundless creativity, showing that the conditions we consider normal for planet formation are merely one chapter in a much larger, more diverse cosmic story. The subtle interplay of light and shadow, the complex gravitational ballet, all combine to form environments that are both breathtakingly beautiful and scientifically profound. There are solar systems where planets orbit in the opposite direction to their star's spin. This phenomenon, known as a retrograde orbit, truly flips our intuition on its head. Instead of gracefully following the general direction of their star's rotation, as most planets in our own familiar system do, some distant worlds swing the other way entirely. It's as if they are rewinding the cosmic clock, moving against the prevailing current of the stellar tide. This backwards motion is a cosmic scar, a record of ancient, often violent, events that reshaped a young system. Such an unusual orbital configuration can arise in several dramatic ways. A planet might be gravitationally tilted, or even entirely flipped, by a close passing companion star or another massive planet in its system during its turbulent youth. Alternatively, it could be torqued by a skewed or highly eccentric protoplanetary disk, where the initial material itself was misaligned with the star's equator. Or, perhaps most violently, it could be jostled during fierce gravitational scuffles, a cosmic game of billiards where worlds collide and ricochet, altering their paths irrevocably. The result of these ancient dramas is an orbital plane that is misaligned with the stellar equator, sometimes by a small, subtle degree, sometimes by a significant tilt, and occasionally, as in the most extreme cases, fully reversed. This peculiar geometry radically reshapes everything about a planet's climate and its tidal forces. Imagine a world where the day and the year, the fundamental cycles of light and darkness, tug in competing directions, creating complex and unpredictable weather patterns. The sun might rise in what we consider the west and set in the east, or perhaps follow a truly bizarre, tilted path across the sky, depending on the degree of misalignment. The tides, pulled by the star, would interact with the planet's rotation in ways that create unique geological stresses and oceanic currents. It's a testament to the universe's ability to create order from apparent disorder, a stable, albeit reversed, path within a system that has endured significant upheaval. Each retrograde world is a case file from a celestial detective story, preserving clues about ancient collisions or distant perturbers that once wandered too close to the system. By meticulously reading these tilted paths, astronomers are able to reconstruct these ancient dramas, piecing together the chaotic history that ordinary, well-behaved orbits would simply hide. These planets prove that their destinies are not always scripted by the neat, predictable spin of their newborn star. Sometimes, destiny is rewritten by a cosmic punch, a gravitational dance that leaves a lasting, beautiful, and utterly perplexing mark on the fabric of a solar system. They are silent witnesses to the universe's dynamic and often violent youth, a reminder that the calm, ordered systems we see today have often emerged from a crucible of chaos. 1 in every 5 sun-like stars may have an Earth-sized planet orbiting it. This stunning statistical revelation emerges from meticulous surveys of dim starlight dips, a method known as the transit method, where scientists observe the subtle dimming of a star's light as a planet passes in front of it. When researchers carefully correct for the limitations of our vantage point and the sensitivity of our instruments, a striking and immensely hopeful pattern begins to emerge around stars that are similar in mass and temperature to our own sun. Roughly a fifth of these sun-like stars appear to host at least one planet that is near the size of Earth. What's even more compelling is that many of these candidate worlds lie in or near what astronomers call the temperate zone, or the habitable zone, where conditions might allow for liquid water to persist on the planet's surface. This doesn't, of course, guarantee vast oceans or a breathable atmosphere filled with oxygen and nitrogen, but it fundamentally transforms the search for potentially life, supporting worlds from a hunt for incredibly rare jewels into a methodical, almost systematic, cataloging of nearby possibilities. The sheer numbers suggest that our galaxy is not just teeming with stars, but also with small, rocky worlds, many of which could, under the right circumstances, harbor the conditions we associate with life. With each new transit measured, and each subtle wobble in a star's motion mapped, a technique, known as the radial velocity method, more and more candidate worlds step forward for deeper, more focused study. Future generations of telescopes, with their vastly improved sensitivities, will not just detect these worlds, but will begin to sift their atmospheres for molecules. They will search for the telltale signatures of water vapor, oxygen, methane, or other compounds that shimmer with the possibility of clouds, winds, and perhaps the intricate biochemistry of living organisms. Imagine the excitement as a distant spectrum reveals a combination of gases that simply cannot be explained by geology alone. The implication of this abundance is profound. It suggests that the night sky, which often appears empty and silent to our unaided eyes, is in fact punctuated by countless small shores. These are worlds, each with its own potential weather, its own unique geological makeup, and its own untold stories. They are waiting for us to develop the tools and the understanding to learn their secrets, to decipher the messages etched into their light. It's a quiet promise that the universe is far richer in planetary diversity, and perhaps in the potential for life, than we ever dared to dream. The cosmic ocean is vast, but it is not empty. It is dotted with islands of possibility, glimmering in the distant light of their parent stars. Some planets wander without a star, set adrift by gravitational encounters, or never tethered to a sun in the first place. These are rogue planets, silent drifters that roam the interstellar dark, unbound by the warmth and light of a parent star. Imagine a world plunged into eternal night, its surface lit only by the faint, diffused starlight from afar, the distant lamps of the galaxy, and warmed predominantly by its own leftover internal heat and the slow, steady decay of radioactive elements within its core. Their skies, if they possess atmospheres, would hold an eternal twilight, a perpetual gloom that knows no sunrise or sunset. Yet, despite this seemingly bleak existence, these solitary worlds may carry thick, insulating atmospheres vast enough to trap what little heat they generate. Or, even more intriguingly, they might harbor buried oceans beneath thick shells of ice, sustained by internal warmth from their formation, or by the subtle, yet powerful, tidal stirring during close flybies of other celestial bodies. These are truly alien environments, where the concept of a habitable zone takes on an entirely new meaning, decoupled from stellar radiation. Detecting these elusive drifters is an immense challenge for astronomers. Because they do not silhouette a parent star in a predictable transit, or cause a noticeable wobble in a star's motion, they are exceptionally difficult to spot. However, careful surveys can sometimes catch their faint, intrinsic glow in infrared wavelengths, or observe the fleeting brightening they cause when, by chance, they pass in front of a distant star. This phenomenon, known as gravitational microlensing, offers a brief, indirect glimpse into their existence as their massive gravity subtly bends the light of a background star. Their existence paints a vivid picture of the dynamic and often violent processes of planetary birth and eviction. It shows that the formation of planets is a common outcome of crowded, young star systems, where gravitational interactions can sling worlds out into the vast, cold emptiness of interstellar space. These lonely worlds transform interstellar space itself into a subtle archipelago, a scattered fleet of cold, dark islands drifting silently between the brilliant lamps of the galaxy. Each one is a testament to the sheer resilience of planetary matter, surviving independently, carrying its own warmth and its own secrets through the endless cosmic night. We have detected solar systems that are almost as old as the universe itself. Imagine stars that formed when the galaxy was in its infancy, barely a few billion years old, enriched by only a few ancestral explosions of earlier, massive stars. Around these venerable, ancient suns, astronomers have found the subtle, yet unmistakable, fingerprints of orbiting planets. The chemistry of these early stars is sparse in heavy elements, anything heavier than hydrogen and helium, compared with modern stars like our Sun. Yet, it was still sufficient for dust to clump and build worlds. This tells us that planet formation is a remarkably efficient process, capable of working with even meager starting materials. These ancient systems have quietly orbited the galactic center for billions upon billions of years, enduring epochs of cosmic history that are almost beyond our comprehension. They have survived countless cosmic mergers, the gentle and not so gentle tidal shuffles of passing stars, and waves of star birth and death that have reshaped the galaxy around them. Their planets, if they still retain atmospheres, have weathered periods of stellar evolution and galactic change that make Earth's entire history seem like a fleeting moment. This immense span of time has given the universe every conceivable chance to test every possible climate tune, every atmospheric composition, and every geological process. These systems are true time capsules, preserving an early recipe for planet formation, a cosmic blueprint that challenges many of our models built from observations of our relatively young, present-day neighborhood. By studying them, we connect the very first chapters of cosmic history with the incredible planetary diversity we observe nearby. It proves that world-making began almost immediately after the first stars lit up the universe, and has been humming along, quietly and consistently, ever since. These ancient worlds offer a glimpse into the primordial conditions of the cosmos, reminding us that the story of planets is as old as the story of stars themselves. They whisper tales of a galaxy long past, a time when the universe was just beginning to find its rhythm, and worlds were already taking shape in the glowing nebulae of creation. Planets can migrate from their birthplace over billions of years. Worlds, it turns out, do not always stay precisely where they first took shape within the swirling, primordial disk of gas and dust. As young planets exchange momentum with this surrounding material, they can slowly, inexorably, drift inward or outward from their original positions, sometimes over vast distances and with dramatic consequences. This process, known as planetary migration, is a fundamental sculptor of solar system architecture. Early in a system's life, while the protoplanetary disk is still rich in gas, a giant planet can experience Type I, or Type A, migration. The friction and gravitational interaction with the disk can cause it to spiral inwards, sometimes quite rapidly. Later, after the gas and dust have largely cleared, gravity games continue, but now between the planets themselves. Worlds tug on one another, exchanging energy, until their orbits stretch, shrink, or even swap places entirely over immense spans of time. Imagine a stately, slow motion ballet, where the dancers subtly adjust their positions over millions of years. This slow, cosmic reshuffling can have profound effects. An icy giant, born in the frigid, distant reaches of the system, might eventually drift inward, settling into a warmer realm closer to its star. Conversely, a massive world might migrate inward, and then outward again, or even park itself in a remarkably close orbit to its sun, becoming a hot Jupiter that could never have formed in its current, searing location. This journey dramatically reshapes the climate and environment of every neighboring world, altering their orbital paths, their energy budgets, and their very destinies. Migration sculpts delicate gravitational resonances where the orbital periods of planets become simple, elegant ratios of one another, like musical notes in harmony. It can also clear vast belts of debris, sweeping them aside or concentrating them into new structures. And, significantly, Migration can trigger showers of comets and asteroids, sending these icy and rocky projectiles hurtling inward to deliver crucial water and organic molecules to inner, potentially habitable worlds. The phenomenon of migration also explains why so many exoplanetary systems defy a simple, inside rocky, outside icy, pattern that we observe in our own solar system. Planetary systems are not static, unchanging structures. They are living, evolving architectures, molded by the gentle, persistent forces of friction and gravity. Their final layouts, the configurations we observe today, carry the deep memory of the currents and encounters of their youth, long after the original, turbulent disk has vanished into the starlight. Each system's architecture is a testament to its unique, dynamic history, a story written in the slow, majestic dance of worlds. Some solar systems are more crowded than ours. Our own solar system, with its wide, open spaces between planetary orbits, might feel vast and uncrowded. But elsewhere in the galaxy, the story can be strikingly different. We find compact families of planets, systems that pack several worlds inside an orbit smaller than that of Mercury, our innermost planet. Each of these worlds races around its star in mere days or weeks, creating a bustling, close, knit cosmic neighborhood. The spacing in these systems can be astonishingly tight, yet they remain remarkably stable, like a string of pearls nested closely together. This stability is not accidental. It arises because the planets likely formed together, or migrated into, balanced and harmonious configurations, settling into gravitational rhythms that prevent catastrophic collisions. In such places, neighboring worlds would loom large in the sky, their phases waxing from slender crescents to full disks within a single week. Imagine the constant, dramatic spectacle of multiple bright orbs traversing the heavens, a dynamic, ever-changing vista. Close quarters amplify tidal forces, stirring atmospheres into complex weather patterns and creating rhythms where planetary conjunctions repeat with the regularity of a cosmic metronome. The gravitational tugs between these closely packed worlds are constant and significant, yet they find a way to coexist, locked in a delicate dance of mutual influence. This crowding does not necessarily mean chaos. On the contrary, if the masses and distances of the planets fall into harmonious ratios, preventing near misses and stabilizing their interactions, these systems reveal that nature often prefers efficiency. Rather than building a few widely spaced giants, the universe can opt to create many medium-sized worlds, distributing them across snug, tightly packed orbital lanes. Their climates and compositions, despite sharing the same central star and being in such close proximity, can still vary dramatically from world to world. One might be a searing hot desert, another a steamy, super Earth with a thick atmosphere, and yet another a mini, Neptune enveloped in a hydrogen-helium shroud. This offers astronomers extraordinary laboratories where a single sunlight feeds a bouquet of planetary experiments, arranged almost shoulder to shoulder. These crowded systems are a powerful reminder that planetary architecture is incredibly diverse, showcasing that the cosmos can fashion stable and complex families of worlds in ways that defy our familiar, spacious understanding. Solar systems can form with no rocky planets at all. Our understanding of planets is often rooted in the familiar, solid ground of Earth. Yet, the universe experiments with far more diverse possibilities. In some distant systems, if the protoplanetary disk is particularly poor in heavy elements, the silicon, iron, and other materials that form rock, or if massive giant worlds form early and hoard much of the available solid material, the inner regions of the system may never assemble durable, solid rock. Instead, gas and ice dominate the available ingredients, yielding a family of many Neptunes or gas giants, with only small, perhaps even insignificant, solid cores. In such rockless systems, the concept of a surface, as we know it, simply doesn't exist. Heat radiating from the central star sculpts puffy, extended atmospheres, turning these worlds into vast, gaseous envelopes. Farther out, in the colder reaches, rings and moons might be carved from icy debris, glittering shards in the dim light. The absence of terrestrial surfaces fundamentally transforms everything about habitability and geology. There are no continents to drift, no volcanic plumes to recycle crustal material, and no shorelines to cradle oceans of liquid water. The very processes that shape Earth's dynamic surface are entirely absent. Yet, even in these gas and ice-dominated environments, chemistry can still thrive. Complex reactions might occur within the swirling, turbulent clouds of the giant planets, or on the surfaces of their icy moons, where cryovolcanism could release exotic compounds. Magnetic fields generated by the deep, churning interiors of these giants could shield their thick atmospheres from the fierce onslaught of stellar winds and radiation, preserving their gaseous envelopes for billions of years. These rockless families demonstrate that planet formation is not obligated to produce Earth analogs. The universe experiments with ensembles where air and ice are the main stage, while stone plays only a hidden, supporting role, buried deep within the crushing pressure of their gaseous hearts. They are a profound reminder of the sheer variety of planetary forms that gravity and chemistry can conjure across the vastness of space. We have found solar systems where planets orbit in perfect harmony. Imagine a cosmic clockwork, meticulously designed, where worlds are locked into synchronized motion, their orbits a precise and elegant dance. These are resonant chains, where for every set number of laps completed by one planet, a neighboring world completes another exact, whole, number count of orbits. This celestial rhythm keeps the orbits from crossing, preventing catastrophic collisions, and can persist for immense spans of time, billions of years, if no major gravitational disturbance arrives to break the spell. This pattern of harmony often forms as planets slowly migrate through the swirling protoplanetary disk. During this process, they can gravitationally capture one another into these synchronized steps, much like dancers subtly adjusting to a shared rhythm on a grand stage. The gravitational tugs become reinforcing rather than disruptive, guiding each world into its designated place within the cosmic ballet. This delicate harmony leaves unmistakable fingerprints in the timing of planetary transits, the dimming of starlight as a planet passes in front. Subtle, periodic shifts in these timings, and the faint, rhythmic tugs planets exchange, allow astronomers to precisely weigh these worlds and even probe their internal structures. For any potential inhabitants, if life were to exist on such a world, the heavens would present a spectacular and utterly predictable display. Regular meetings of bright companions, their phases changing in a precise, repeating sequence, would be spaced like notes in a repeating melody. Conjunctions and oppositions would occur with unwavering regularity, shaping cultural calendars and perhaps even giving rise to unique astronomical mythologies. Such systems show that gravity, when given enough time and gentle friction within a formative disk, can compose stable, enduring music from the raw materials of dust and gas. The result is not rigid or fragile, but resilient, a natural cadence that reveals the deep history of planetary migration written into the very beat of the years. They are a testament to the universe's capacity for creating profound and enduring order out of the most fundamental forces. Some solar systems are full of planets that are all about the same size. In our own solar system, the planets vary dramatically in scale, from the tiny, rocky Mercury to the colossal, gaseous Jupiter. But elsewhere, the story can look remarkably different. In several observed systems, all of the known planets are unexpectedly close in size, as though stamped from a cosmic mold. These worlds usually fall somewhere between the diameter of Earth and Neptune, forming a harmonious family of super-Earths, or mini-Neptunes, lined up in tight, compact orbits around their parent star. Despite this striking uniformity in size, their individual surfaces and atmospheres can still differ wildly. These variations depend on a multitude of factors: their precise position relative to the star, the unique chemistry of the protoplanetary disk from which they formed, and the specific histories of collision and migration that shaped each one. One might be a scorching, rocky world, another a warm, watery ocean planet, and a third a mini, gas giant with a thick, steamy atmosphere. This kind of uniformity in size suggests specific formation conditions that might distribute material more evenly within the protoplanetary disk, or gravitational interactions that keep competing planets in check, preventing any single world from dominating and accreting vastly more mass than its siblings. Such systems profoundly challenge our sense of what is normal in planetary architecture. Instead of the familiar pattern of a few giants and a few small ones, the universe, in these cases, appears to prefer a form of symmetry, a more evenly distributed collection of worlds. They open fascinating questions about whether life, bearing stability, might be more common in evenly balanced systems. In such systems, no single, massive world dominates the gravitational landscape, potentially leading to more predictable and less chaotic long-term orbital dynamics. They are a vivid illustration of the universe's immense creative palette, showing that planetary families can be assembled in countless unexpected and elegant ways, each system a unique expression of cosmic possibility. There are solar systems where planets skim so close to their stars that metal can vaporize. Imagine a world where the concept of solid ground is a fleeting illusion. Some planets race around their stars at distances so incredibly short that a full year, their entire orbital period, lasts only a matter of hours or days. On these ultra-hot Jupiters, or lava worlds, daytime temperatures can soar to such scorching levels that they are high enough to vaporize iron, silicates, and other refractory metals that form the very bedrock of planets. On such extreme worlds, rocky mountains, as we understand them, might never truly form. The constituent ingredients for stone can sublimate directly into the atmosphere, bypassing a stable solid phase entirely. Imagine towering, supersonic winds, whipping clouds of metal vapor from the perpetually irradiated day side to the cooler, perpetually dark night side. On the night side, these shimmering metallic gases would condense, forming glittering mineral clouds that might rain molten droplets of iron, titanium, or other heavy elements back toward the surface. The sky would be a maelstrom of metallic rain and gaseous rock, a truly alien form of weather. These extreme environments push the very outer limits of planetary survival under fierce stellar radiation. They are cosmic crucibles, revealing how atmospheres behave when chemistry is pushed far beyond familiar ranges, creating exotic weather cycles that have no counterpart anywhere on Earth. The existence of such worlds shows us that planet formation is not deterred by the furnace of a star's intense heat. Rather, it adapts to it, building strange, resilient spheres that endure in places we once thought entirely hostile to any form of solid matter. They are a testament to the sheer toughness of planetary material, clinging together and enduring in conditions that would instantly annihilate anything from our own temperate neighborhood. We have found solar systems with planets that have no atmosphere. Not every world manages to cling to its surrounding veil of gases, that precious blanket of air that sustains life on Earth. Some planets are being relentlessly stripped bare by the brutal onslaught of stellar winds, intense radiation, and the gravitational tugs of their parent stars or close companions. Close, orbiting rocky planets are especially vulnerable to this atmospheric erosion. Energetic particles blasted from their star can literally chip away at their surfaces, blasting molecules and atoms into space until little remains but a naked, pockmarked rock. Without an atmosphere to moderate temperature, the day side of such a planet can bake under unrelenting stellar glare, reaching scorching temperatures, while the night side, perpetually cast in shadow, freezes to near absolute zero. Imagine a world locked in a brutal, uncompromising tug of war between scorching light and icy shadow, with no moderating blanket of air. The lack of an atmosphere also means no weather, no gentle breezes or life-giving rains. It means no protection from the constant barrage of meteoroid impacts, leaving the surface heavily cratered and exposed. And crucially, it means no medium for sound to travel, rendering these worlds utterly silent, their cosmic silence unbroken by wind or wave. Yet, these stark, airless bodies are not without their scientific value. Their exposed surfaces become a direct, unclouded record of the world's history, preserving geological features and impact craters without the blurring effects of erosion or atmospheric chemistry. By studying these silent, bare worlds, astronomers learn invaluable lessons about how atmospheres are lost, what crucial roles magnetic fields play in shielding planets from stellar assault, and just how fragile the delicate balance of pressure and temperature can be for a world to retain its sky. Even in their profound silence, these airless planets speak volumes about the struggle to hold onto a sky, a poignant reminder of the preciousness of Earth's own ethereal veil. Some planets form far from their star and only later move inward. A planet's birthplace, it turns out, is not always its final address in the grand cosmic scheme. Far from the searing heat of a star, in the cold, distant outskirts of a young, swirling protoplanetary disk, ices and dust can more easily clump together. Here, the conditions are ripe for building hefty cores, the foundational building blocks of giant planets. These nascent worlds then begin a slow, majestic drift inward, like colossal rafts on a river of gas and dust. This gradual migration can occur through various mechanisms. One primary driver is the subtle, yet persistent, drag from the surrounding gas and dust of the disk itself. As the planet orbits, it creates density waves in the disk, which in turn exert a gravitational torque on the planet, either pushing it inward or, less commonly, outward. Alternatively, gravitational nudges from neighboring worlds or resonant interactions can slowly but surely alter a planet's orbital path. A giant planet, perhaps a gas giant like Jupiter or a massive ice giant like Neptune, born in the frigid depths of space, might eventually settle into a tight orbit close to its star, becoming a hot Jupiter that could never have formed in its current, scorching location. This inward journey dramatically reshapes the entire architecture of the system. Such a migrating giant can act like a cosmic snowplow, potentially sweeping aside smaller, inner worlds or scattering belts of debris into chaotic showers of comets and asteroids. The inward traveler can also trigger powerful gravitational resonances, locking other planets into synchronized, predictable paths, fundamentally altering the system's long-term stability. By meticulously tracing these migratory footprints, researchers can decode the hidden, dynamic past of systems that appear static and serene today. Planetary placement, therefore, is not a birth certificate, but rather a snapshot of a moment in cosmic time. Many worlds carry the deep, etched memory of a long inward voyage beneath their swirling clouds, a silent testament to the dynamic and ever-changing nature of planetary systems. Their journey shapes not only their own destiny, but the destinies of all their celestial neighbors, creating a complex, interwoven history that defines the unique character of each solar system. Solar systems can be destroyed when stars become supernovas. When a truly massive star, one many times the size of our Sun, reaches the end of its life, it does not simply fade away. Instead, it can explode with a brilliance that, for a brief, terrifying moment, outshines entire galaxies. This cataclysmic detonation, known as a supernova, unleashes shock waves of incomprehensible power, capable of tearing apart nearby planets, vaporizing their atmospheres, and hurling their shattered debris into the cold, silent expanse of interstellar space. Even worlds that are not directly shattered by the initial blast may be utterly sterilized by the intense, ionizing radiation that floods the system. Their delicate atmospheric chemistry would be rewritten in an instant, their surfaces baked and irradiated beyond recognition. The immense blast can also carve expanding bubbles through the surrounding interstellar gas, triggering new star and planet formation in distant regions, while abruptly ending it in the star's own immediate neighborhood. It's a cosmic paradox, destruction leading to creation elsewhere. Some planetary fragments, perhaps super dense cores or particularly resilient rocky remnants, might survive the initial cataclysm. These forlorn pieces of what were once thriving worlds would then become orphaned asteroids or molten, dark cores, wandering the vast void without a sun to guide them, silent ghosts of a vanished system. Studying these cataclysmic endings offers an invaluable glimpse into the grand recycling of cosmic material. The heavy elements forged in the heart of the dying star, the iron, nickel, gold, and uranium that are essential for rocky planets and, ultimately, for life, will eventually be scattered and reincorporated into new nebulae, seeding future generations of stars and their accompanying planetary systems. Solar systems, then, are not eternal. They are not fixed, unchanging entities. Instead, they are chapters in a vast, ongoing cycle of creation and destruction, a grand cosmic narrative written across the boundless expanse of the galaxy. Each supernova is a punctuation mark, ending one story while providing the raw material for countless others, ensuring that the universe remains a dynamic, ever-evolving tapestry of matter and energy. There are solar systems with planetary rings bigger than stars. When we think of rings, our minds usually conjure images of Saturn's elegant, icy halos. But rings are not just for Saturn, and their scale can be truly astonishing. Some exoplanets, distant worlds orbiting other stars, boast ring systems so incredibly vast that their total diameter would dwarf even a medium-sized star such as our Sun. Imagine a planet encircled by a structure so immense it could eclipse an entire star from certain perspectives. These colossal structures may form from a variety of dramatic events: the catastrophic shattering of multiple moons through violent collisions, the capture and subsequent breakup of numerous comets, or simply from leftover debris in the protoplanetary disk that never fully coalesced into a companion body. When such a ringed planet transits its star, that is, passes in front of it from our vantage point, the rings can block a significant amount of starlight long before and after the planet itself passes. This creates peculiar, drawn-out dips in brightness that first alerted astronomers to their incredible scale, a signature unlike anything produced by a simple spherical planet. The sheer size and mass of these rings present profound challenges to our current models of stability. How do such wide, diffuse disks resist collapse, or prevent themselves from spreading too thin or evaporating entirely over millions of years? Their presence hints at dynamic and often recent histories, perhaps involving powerful tidal breakups of larger moons or colossal impacts that created immense quantities of debris. If a moon were to form within such a ring system, it might eventually clear a lane, growing larger and larger until it becomes a fully fledged, ring-shepherding companion, much like some of Saturn's moons. These oversized halos are a breathtaking reminder that even familiar features like rings can reach truly unimaginable proportions when gravity and time are given the right raw materials. They stretch our understanding of what a planetary system can encompass, proving that the universe is far more inventive and grand in its designs than our local experience might suggest. They are silent, glittering monuments to cosmic upheaval and the persistent beauty of matter arranged on a colossal scale. Some solar systems contain moons larger than Earth. Moons, in our familiar solar system, are often thought of as minor companions, dwarfed by their colossal gas giant parents. However, in the distant reaches of the galaxy, the story of satellites can be radically different. In some distant systems, a moon can rival or even exceed Earth in its sheer size and mass, truly orbiting a giant planet like a world in its own right, a colossal sentinel in the shadow of its even larger host. These exomoons, if confirmed, would represent a significant expansion of what we consider a world. They may harbor thick atmospheres, vast liquid oceans, and complex geological activity, all powered not just by the distant light of their star, but profoundly by the intense tidal heating generated by the gravitational pull of both their massive host planet and the central star. Imagine a moon constantly kneaded and squeezed by immense gravitational forces, generating internal friction that could melt rock, drive volcanism, and sustain subsurface oceans. The day length on such a massive moon would depend on a delicate balance of its orbital motion around the planet and its own rotation, creating unusual and often extended cycles of light and shadow. The sky might be dominated by the colossal disk of its parent gas giant, a breathtaking spectacle of swirling colors and atmospheric bands, casting ever-changing light onto the moon's surface. Detecting such moons is an immense observational challenge. Their faint signals are often blended with, or completely overwhelmed by, the much brighter light of their host planets and stars. However, astronomers are developing sophisticated techniques, looking for subtle timing shifts in the transit of the planet, or minute flickers of starlight that could betray the gravitational presence of an orbiting satellite. If confirmed, these giant moons would fundamentally expand the concept of habitable zones. No longer would we only look for life on planets orbiting within this temperate band. Instead, the search would broaden to include the satellites of gas giants, where a moon with Earth-like mass and the presence of water could potentially thrive. Such a moon could benefit from the protective magnetosphere of its parent planet, shielding it from harsh stellar radiation, while simultaneously receiving warmth from both the star and reflected light from the giant planet itself. The discovery of such a place would redefine where we look for life, how we imagine homes beyond Earth, and illustrate the incredible ingenuity of the universe in fostering potential oases in unexpected corners of the cosmos. These super-sized moons are not merely companions, they are worlds unto themselves, each a potential stage for new forms of existence. We have found solar systems with planets that have no moons at all, while our Earth is graced by a single, familiar moon, and Jupiter boasts a celestial court of dozens. Some planets in the vast expanse of the cosmos roam their orbits in utter solitude. They are utterly alone, without even a small, captured rock or a gravitationally bound companion to accompany them on their long journey around their star. The absence of moons on such worlds can be the result of a violent past, where catastrophic collisions ejected or destroyed any early satellites that might have formed. Or it could stem from a quieter, more barren birth in regions of the protoplanetary disk that were simply too sparse in material to build them. Without the steadying gravitational influence of a moon, a planet's axial tilt, the angle at which it spins relative to its orbit may wobble more dramatically through time. This can lead to erratic and extreme seasonal changes, creating climate swings that could be devastating for any developing life. Tides, driven solely by the distant star, would be significantly gentler, reshaping coastlines more slowly and reducing the tidal heating that can fuel geological activity and internal warmth, particularly crucial for icy worlds. The night sky on such a moonless planet would appear stark, empty, and profoundly dark, with no secondary light source to soften the blackness or cast eerie shadows across the landscape. Yet, The very solitude of these planets offers a pristine laboratory for studying internal dynamics without the complicating, often chaotic, tug of a companion. Scientists can observe how their rotation, geology, and atmospheric processes unfold, free from external lunar influences. Their very emptiness poses intriguing questions about the ingredients and specific processes that favor moon making. What conditions are necessary to form, or to capture, a stable satellite? What percentage of planets go through their entire existence without a celestial partner? In the great variety of solar systems across the galaxy, even a missing moon tells a compelling story about chance, collision, and the subtle scarcity of cosmic circumstances. These silent, companionless worlds are a stark contrast to our own, reminding us of the unique and often overlooked role our moon plays in shaping Earth's environment. Some planets have moons that formed before their planet did. This is a truly counterintuitive concept, flipping the conventional understanding of planetary formation on its head. In rare and intriguing cases, a celestial body that we now classify as a moon may actually predate the very planet it orbits. It might have been born as an independent, free-floating object in the vast, swirling protoplanetary disk, or perhaps it was a passing body, captured from interstellar debris, long before its main world even finished assembling itself. Later, as material slowly gathered and accreted into the nascent planet, gravity eventually pulled this older, independent object into a stable orbit, transforming a former wanderer into a permanent satellite. Such ancient moons carry distinct chemical and isotopic signatures that differ significantly from their younger host planet. They are like cosmic fossils, preserving a unique record of earlier conditions in the protoplanetary disk, or even of a completely different region of space. Their heavily cratered surfaces and deep, seeded layers might reveal a history of impacts and radiation exposure from eras that the planet itself never experienced, having formed later and perhaps in a more protected environment. Imagine a moon whose surface tells a story billions of years older than the planet beneath it. This fascinating reversal of roles blurs the traditional line between what we define as a planet and what we define as a moon. It shows that the order and hierarchy we perceive in a solar system are often a matter of timing, gravitational capture, and historical circumstance, rather than a strict, predefined lineage. Studying these mismatched pairs deepens our understanding of how celestial bodies exchange places, how gravitational interactions can lead to unexpected pairings, and how early formation stages can overlap and unfold in truly surprising ways. These firstborn moons are silent, ancient witnesses to the tumultuous birth of their systems, carrying within their very structure the echoes of a distant past, a cosmic secret waiting to be deciphered. The first exoplanets were found orbiting a dead star. Before the groundbreaking discovery of planets orbiting vibrant, sun-like stars, the very first confirmed detections of worlds beyond our solar system came from an entirely unexpected source, a pulsar. A pulsar is the incredibly dense, rapidly spinning core left behind after a massive star has met its violent end in a supernova explosion. This stellar remnant emits incredibly precise beams of radio waves with clock-like regularity, making it an ideal cosmic timer. Tiny, yet rhythmic, deviations in the timing of those pulses revealed the subtle gravitational pull of orbiting planets. These were not just any planets. These were bodies that had somehow survived the cataclysmic death of their star, or perhaps reformed from the scattered debris in the aftermath of the supernova. These worlds now endure in a realm flooded by intense radiation, bathed in the eerie, pulsating glow of a rapidly rotating neutron star, an environment that seems utterly hostile to any form of conventional planetary existence. Their existence was a seismic shock to the scientific community. It proved, beyond a shadow of a doubt, that planets can arise and persist in the most unlikely and extreme environments. It demonstrated that planet formation, or indeed, planet recycling, can occur even after the most cataclysmic events in the universe. This discovery shattered long-held assumptions about where and how planets could form, fundamentally opening up the entire field of exoplanet science. It showed that nature, in its boundless creativity, writes planetary stories in places far stranger, far more resilient, and far more unexpected than our gentle, familiar solar neighborhood. Every subsequent exoplanet discovery, every new world added to our cosmic catalog, traces its lineage back to those first, improbable worlds circling a dead sun, a testament to the universe's capacity for surprise and endurance. Some solar systems have planets that orbit faster than a day on Earth. Imagine a year that flashes by in less time than it takes our planet to complete a single rotation, to experience one sunrise and one sunset. In some distant solar systems, a planet can achieve this astonishing feat. These ultra-short period planets are locked in orbits so incredibly close to their parent stars that they race around them in a frantic, dizzying loop, sometimes completing an entire revolution in less than 10 Earth hours. Their incredibly swift motion is governed by extreme gravity and blazing, incandescent heat from their nearby star. This proximity leads to atmospheres that are constantly boiling away or shifting between states of vapor and plasma, a dynamic, ephemeral veil of gas. The tidal forces exerted by the star are immense, stretching and squeezing these planets, creating intense internal friction that can melt rock and drive volcanic activity on a scale we can barely comprehend. If one could somehow stand on the surface of such a world, the parent star might fill half the sky, a blazing, overwhelming presence. The sheer speed of the orbit would cause dramatic and rapid changes in light and temperature across the landscape, even if the planet is tidally locked. Indeed, many of these blisteringly fast worlds are tidally locked, meaning one hemisphere is perpetually exposed to the fierce stellar fire, while the other is cast into eternal, unforgiving shadow. The boundary between these two extremes would be a zone of unimaginable atmospheric turbulence and temperature gradients. Their blistering orbits hurtle through warped spacetime, illustrating the sheer range of planetary environments that can exist when nature pushes the laws of physics to their most dramatic and extreme tests. These planets are not just fast, they are a testament to the boundaries of orbital stability and planetary endurance, demonstrating just how much punishment a world can withstand and still maintain its integrity, albeit in a spectacularly alien form. We have detected exoplanets that are mostly water. Imagine a world where the concept of land simply does not exist, a planet made almost entirely of water, existing as a global ocean of unimaginable depth. Some worlds beyond our solar system appear to fit this extraordinary description. Their immense, dense, pressurized layers of water may transition from familiar liquid to exotic, alien forms of ice unseen on Earth. These include Ice-Theau or Ice-X, where water molecules crystallize in incredibly compact cages under unimaginable pressures, forming solid structures at temperatures far above what we consider freezing. Above this colossal watery core lies an atmosphere filled with superheated steam or vapor, possibly enveloped by thick, reflective clouds. These clouds could reflect a high percentage of the star's light, giving the planet a pale, ethereal blue halo when observed from afar, a shimmering pearl in the cosmic ocean. These water worlds may experience constant, planet-spanning storms, with winds sweeping uninterrupted across oceans thousands of kilometers wide, never encountering a landmass to break their fury. The concept that a planet can form and survive without a significant rocky crust beneath its vast ocean expands our very definition of habitability. It suggests that life, if it evolved there, might have no concept of land at all, thriving in vast, three-dimensional underwater ecosystems completely alien to anything humanity has ever imagined. On such a world, plate tectonics and volcanism, the geological forces that shape Earth, would happen beneath kilometers of crushing, super-pressurized sea, creating submarine mountain ranges and hydrothermal vents that could be potential cradles for unique forms of life. These planets are a powerful reminder that our Earth-centric view of what constitutes a world is far too narrow. The universe, in its boundless creativity, can craft entire spheres from the most common of molecules, transforming water into a fundamental building block of planetary architecture, creating worlds that are truly oceanic in every sense of the word. There are solar systems where the planets are made of diamond. The very idea conjures images of unimaginable wealth and dazzling beauty. Some planetary bodies have been detected with densities and compositional signatures that strongly imply they are incredibly rich in carbon. And, under the right conditions of immense temperature and crushing pressure, carbon can crystallize into its most exquisite and durable form, diamond. These so-called diamond worlds likely formed around stars that were themselves unusually rich in carbon-bearing material, allowing for this element to dominate the early protoplanetary disks. As these planets cooled and compressed over aeons, their interiors may have transformed into vast, glittering layers of solid diamond, extending for thousands of kilometers. These deep diamond mantles could be capped by oceans of molten carbon, or even by thick, carbon dioxide-rich atmospheres, creating an environment utterly alien to our experience. Temperatures on the surface might be sweltering hot or freezing cold, depending on the planet's distance from its star, but deep below, the internal pressures would ensure the carbon remained in its crystalline form. Such worlds could potentially contain more diamond than has ever existed in the entire history of Earth, turning the concept of terrestrial treasure into something truly cosmic in scale. Imagine entire geological strata composed of glittering gems, a testament to the universe's ability to create beauty from the most fundamental elements. These planets remind us that beauty, value, and geology take on unimaginable forms across the galaxy. While elements follow universal laws of physics and chemistry, the outcomes are anything but ordinary, creating worlds that are as scientifically fascinating as they are aesthetically breathtaking. They are silent, shining jewels in the cosmic dark, each a unique masterpiece of elemental transformation. Some planets orbit so close to their star that a year lasts only hours. In several star systems, astronomers have found planets locked in such incredibly tight orbits around their host stars that their orbital periods are unbelievably short, mere hours long. They complete entire revolutions in the time it takes us to eat breakfast, or to sleep through a single night. These planets exist in a state of perpetual, blistering heat. Their sun-facing sides are heated to thousands of degrees, causing rock to vaporize and form atmospheres of mineral gases. Their skies might shimmer with clouds of silicate particles, reflecting the intense stellar glare in a dazzling, alien display. Metal, such as iron, could condense in these upper atmospheres and rain down as droplets of molten iron, creating a truly hellish precipitation. The intense stellar radiation continuously strips these atmospheres away, leaving long, comet-like tails trailing behind the planet as they furiously race around their star. These tails are visible evidence of a world slowly eroding, losing its very substance to the relentless power of its sun. The gravitational pull from their star is so overwhelming that many of these planets are tidally locked. This means one hemisphere is forever exposed to the scorching stellar fire, a perpetual day side, while the other is cast into eternal, unforgiving shadow, a never-ending night. Their blistering orbits hurtle through warped spacetime, illustrating the sheer range of planetary environments that can exist when nature puts the laws of physics to their most dramatic and extreme test. These are not just hot planets, they are worlds living on the edge of cosmic destruction, a testament to the incredible forces at play in the universe, and the resilience of matter even under the most unimaginable conditions. We have detected planets as light as cork. Among the vast and ever-growing catalog of exoplanets, some truly defy our conventional expectations of what a planet should be. A peculiar class of worlds has been discovered that are so puffy and lightweight that, if such a thing were cosmically possible, they would theoretically float in water. These planets have extremely low densities, often less than that of cork itself. This is due to their enormous sizes combined with incredibly bloated, extended atmospheres, primarily composed of hydrogen and helium. These celestial oddities are affectionately known as super puffs or cotton candy planets. They typically orbit quite close to their stars, where the intense stellar heat expands their gaseous envelopes to enormous volumes, giving them their remarkably low densities. Despite their impressive radii, some rivaling Jupiter in size, their total mass might only equal a few Earths, making them incredibly fragile and ethereal. The slightest increase in stellar radiation, or a close gravitational encounter with another object, could potentially strip away their tenuous atmospheres completely, leaving behind a much smaller, denser core. This strange, low-density state profoundly challenges our current understanding of planetary formation. It suggests that these worlds either formed incredibly quickly, accreting vast amounts of gas around relatively small frozen cores, or perhaps accumulated their gaseous envelopes slowly and gently in more serene environments, before later drifting inward to their current, warmer orbits. Their existence vividly demonstrates how delicately balanced a planet can be, surviving only because the universe allows it a rare and narrow set of circumstances. These super puffs are like cosmic bubbles, delicate and vast, floating through the stellar winds, a unique expression of planetary physics at its most extreme and surprising. Some solar systems have planets far more massive than Jupiter. Our own Jupiter is the undisputed heavyweight champion of our solar system, a colossal gas giant that dwarfs all other planets combined. Yet, in other stellar systems across the galaxy, the story of planetary scale can make Jupiter look modest by comparison. These super Jupiters can be 10 or even 20 times more massive than our largest planet, and yet still qualify as planets because they are not quite large enough to ignite the sustained nuclear fusion reactions that would turn them into stars. Their immense gravity can profoundly dominate an entire system, acting as a cosmic orchestrator. They can steer the orbits of neighboring, smaller planets, sculpt vast debris belts into intricate patterns, and even prevent smaller worlds from forming at all by sweeping up or scattering potential building blocks. Their atmospheres may be crushingly dense, filled with exotic chemistry driven by immense internal pressures and the lingering heat left over from their formation. Imagine a world where the atmosphere itself is so compressed it behaves more like a liquid, with chemical reactions occurring under conditions utterly alien to Earth. Some of these colossal giants orbit incredibly close to their stars, becoming searing hot and glowing faintly in infrared wavelengths, radiating their internal heat into space. Others roam far out in the frozen dark, with cloud tops colder than any temperature recorded on Earth, vast, silent behemoths shrouded in icy hazes. The sheer scale of these worlds stretches the very word, planet, to its limit, showing that even within a broadly defined category, the universe permits an extraordinary diversity of size, mass, and internal structure. These super Jupiters are a testament to the boundless creativity of gravity, capable of assembling worlds of truly gargantuan proportions. We have found planets that orbit more than one star at a time. While our Earth orbits a single, solitary star, a familiar and reassuring constant, Some planets in the cosmos follow much more complex and dynamic paths. They orbit around multiple suns, circling them as a gravitational unit, engaged in a perpetual celestial dance. These circumbinary, or circumulipal, worlds experience a truly intricate gravitational ballet, where the star system itself twists, turns, and wobbles through space, even as the planet maintains a wide, stable orbit around the entire stellar ensemble. The skies of such a world would be a spectacle of shifting light and shadow. Imagine 2 or even 3 sunrises and sunsets each day, their positions and relative brightness constantly changing as the stars interact and move through their own orbital dance. Temperatures on the surface would rise and fall in strange, often unpredictable cycles, defined not only by the planet's distance to a primary star, but by the ever-shifting gravitational influence and radiant output of its stellar companions. The light would ebb and flow, creating complex weather patterns and unique challenges for any life attempting to adapt. These planets are remarkable survivors. They formed and endured through the chaotic birth of a multi-star system, where the intense gravitational turbulence could have easily ejected them into the cold, silent void of interstellar space. Instead, they found a delicate balance, circling a gravitational center that itself drifts through the cosmos like a complex, living system. These planets show that stability is still possible, even in what appears to be a chaotic environment. They demonstrate that the universe's fundamental rules always find a way to carve harmony out of complexity, creating stable, enduring worlds amidst a backdrop of multiple, interacting suns. They are a testament to the intricate and beautiful solutions that gravity can devise, allowing for worlds to exist in the embrace of not one, but many stars. Some solar systems are hidden inside star clusters. Star clusters are dense, glittering neighborhoods in the galaxy, places where thousands, or even hundreds of thousands, of stars formed together in a single, colossal burst. They are packed so tightly that the night sky on any planet within such a cluster would glow with countless suns, a perpetual twilight rather than true darkness. For a long time, astronomers wondered if planets could even survive in such busy, gravitationally turbulent environments, where passing stars might strip them away or disrupt their orbits with frequent close encounters. Yet, observations have revealed a fascinating truth. Planets can indeed be found nestled within these stellar cities. They orbit their parent stars in relative peace, their gravitational bonds strong enough to withstand the gravitational nudges of their many neighbors. While these planets may experience close encounters with other stars every few million years, events that might subtly change their climates or even their orbital positions, many endure for billions of years, a testament to the robustness of planetary formation. Their existence suggests that the process of planetary formation is incredibly resilient, capable of unfolding even in crowded, energetic nurseries where radiation, gravity, and constant stellar motion collide. To stand on such a world would be to witness a sky blazing with starlight, a breathtaking panorama where the cosmos never truly grows dark. Imagine constellations of hundreds of bright stars, each a nearby sun, casting complex shadows and creating a multi-layered light show. Life on such a world would share its space with the very furnaces of young suns, adapting to a sky that is a perpetual, glittering twilight. These cluster-born systems offer a unique perspective on habitability, showing that worlds can thrive even in the most luminous and densely packed corners of the galaxy. Solar systems can be disrupted by passing stars. Stars, like ships on a vast cosmic ocean, travel through the galaxy in perpetual motion, and sometimes their paths bring them dangerously close to one another. When a passing star swings near a solar system, its immense gravity can exert a powerful tug on planets, asteroids, and comets, subtly, or sometimes dramatically, reshuffling their orbits. This kind of gravitational disturbance can even eject entire worlds into the cold, silent expanse of interstellar space, turning them into rogue planets. This cosmic close encounter may send icy bodies from the distant outer reaches of the system plunging inward, triggering periods of intense cometary bombardment on inner planets. Or it could pull distant worlds into new, highly eccentric orbits that dramatically change their climates, perhaps pushing them from a temperate zone into an icy exile, or vice versa. Some planets might be completely lost, gravitationally slung into the void to become solitary wanderers. These encounters, while rare on human timescales, are practically guaranteed to occur over the billions of years of a star's lifetime. The fossil record of such a disruptive event may be seen in the oddly tilted or highly eccentric orbits of a system's remaining planets, or in the presence of scattered, chaotic debris belts. These subtle clues suggest that the apparent quietness and order of our own solar system might itself be, in part, a stroke of cosmic luck, a testament to a relatively undisturbed past. Such disruptions remind us that solar systems are not isolated, unchanging islands in space. Rather, they are dynamic travelers within a vast, living galaxy, constantly shaped by gravitational encounters that we cannot yet see, but whose effects are etched into the very fabric of their planetary architecture. They are a reminder that the universe is a place of constant motion and subtle, yet powerful, interactions. Some planets form in the debris disks left behind by dead stars. When a star like our Sun reaches the end of its life, it doesn't always go out with a bang. Instead, it can die gently, shedding its outer layers to become a quiet, incredibly dense white dwarf. But sometimes, this dying process leaves behind a swirling, ghostly disk of gas, dust, and the shattered remains of earlier planets that were too close to survive the star's expansion. Within this ethereal disk, amidst the cosmic ashes, new planets can begin to form, recycling the materials of a previous generation. These, second chance worlds, are remarkable. They may contain elements forged in the very heart of the dying star, giving them an unusual chemical composition or exceptionally dense metallic cores. Their parent star, now a white dwarf, no longer burns with the fierce light of a main sequence sun. Instead, it glows faintly with leftover heat, casting a dim, reddish light across a landscape that might still hold warmth deep underground, sustained by internal radioactivity. The idea that planets can be born from the literal ashes of their predecessors fundamentally expands our understanding of the life cycle of solar systems. It proves that destruction can also be a profound kind of creation, a cosmic reincarnation. These reborn worlds occupy a twilight realm of astrophysics, a place where the end of one cosmic story becomes the intriguing prologue to another. They are a testament to the universe's tireless ability to recycle its materials, to find new pathways for creation even in the wake of stellar death. Studying these systems offers a unique window into the long-term evolution of stellar remnants and the surprising resilience of planet formation, showing that even a dead star can still be apparent to new worlds, albeit in a hauntingly different kind of light. Solar systems can be born from collisions between giant clouds of gas. Imagine two colossal, diffuse clouds of gas drifting silently through the emptiness of a galaxy. When these immense structures intersect, sometimes with enough force, the collision itself can trigger a cascade of star formation. The impact compresses the hydrogen, helium, and interstellar dust within the clouds, creating dense pockets that begin to collapse under their own gravity. These compressed pockets become the fertile cradles of new stars, each potentially surrounded by its own swirling disk of material where planets may eventually emerge. This dramatic, violent beginning leaves distinct fingerprints on the systems that eventually form. The initial turbulence of the collision can result in planets with wildly tilted orbits, unusual spacing, or unexpected chemical makeups, reflecting the chaotic conditions of their birth. Some planets may form quickly and grow massive before the initial chaos fully settles, while others might emerge later from the leftover debris, taking shape in a more subdued environment. Even the stars themselves might be born as siblings, traveling through space together, each with its own retinue of worlds, a family born from a single, grand cosmic impact. This kind of cosmic collision demonstrates that star and planet formation is not always a calm, gentle process. Sometimes it begins with an interstellar impact, a grand, violent event that sets the stage for the birth of entire families of worlds. It shows the dynamic and often aggressive nature of galactic processes, where collisions on a truly massive scale can be the very catalyst for new life and new systems. These systems are a testament to the universe's capacity for dramatic creation, where the most beautiful and complex structures can arise from the most violent of beginnings. There are solar systems where dust clouds never fully become planets. Not every protoplanetary disk, that swirling, fertile cradle of gas and dust around a young star, successfully coalesces into a complete set of solid worlds. In some solar systems, the dust and gas remain in a suspended swirl for billions of years, a perpetual state of almost formation. These translucent, glowing clouds reflect the light of their star, revealing a stalled process of planetary birth, a cosmic blueprint that was never fully realized. Perhaps the disk lacked enough initial mass, or early gravitational disturbances from nearby stars prevented larger bodies from forming. In other cases, unseen planets may lurk within these clouds, their gravity shepherding the dust into intricate rings and lanes, creating subtle patterns without ever fully clearing a path or growing into fully fledged worlds. These half-formed systems act like cosmic time capsules, preserving the raw ingredients of planet, making long after neighboring systems have moved on to rocky surfaces, deep oceans, and atmospheric storms. They are snapshots of a process frozen in time, a perpetual adolescence. These lingering clouds also play a role in the broader galactic ecosystem. They slowly replenish the interstellar medium, sending fine dust back into space, where it might one day seed the next generation of stars and planets. Studying these persistent, half-formed systems helps scientists understand the delicate balance required for planets to emerge, and why some stars never end up with full-fledged worlds at all. It highlights the precise conditions of mass, stability, and timing that are necessary for the universe to complete its grand act of planetary creation. These quiet, dusty systems are reminders that even the most promising beginnings can sometimes lead to an unfulfilled destiny, a beautiful, swirling testament to cosmic possibility that never quite solidified. Some planets orbit far beyond the reach of their star's light. In the vast, silent outskirts of certain solar systems, lurk planets so incredibly distant that their host star appears merely as a bright speck in the sky, barely distinguishable from other stars. These worlds move through regions where warmth from the star scarcely reaches, plunging their surfaces into bitter, perpetual cold, a realm of eternal deep freeze. Any atmosphere they might retain would be incredibly tenuous, or would largely freeze into layers of ice, slowly stacking over centuries until only slivers of gas remain aloft. Water, if present, would be solid rock, and oceans would be vast, frozen plains. Yet, even in these frigid, distant reaches, some of these giants may harbor internal heat. This warmth could come from radioactive decay within their cores, or from the lingering energy of their violent birth. This internal heat could create subsurface oceans beneath thick, frozen crusts, protected from the harsh cold of space. Their slow, monumental orbits can take thousands of Earth years to complete, making their seasons longer than the entire recorded history of human civilization. Imagine an entire epoch of human history unfolding during a single, imperceptible shift in the angle of sunlight. These remote worlds serve as a powerful reminder that the architecture of a solar system can stretch far beyond the cozy, temperate zones where warmth and light create familiar, life-supporting landscapes. In those distant, icy reaches, alien chemistry and immense planetary endurance replace sunlight as the ruling forces of planetary life, shaping worlds in ways that challenge our most fundamental assumptions about celestial existence. They are silent, frozen sentinels, guarding the distant edges of their stellar domains. We have found planets that orbit their star on a tilted axis. Most planets, including those in our own solar system, orbit roughly in line with the equator of their star, following the general direction and angle that their protostellar disk originally spun. But some distant worlds defy this neat pattern, tilting wildly above or below the stellar plane, their orbital paths skewed at dramatic angles. These misaligned orbits suggest a chaotic and often violent past, a history of gravitational upheaval that fundamentally reshaped their destinies. Such a severe tilt could be caused by powerful collisions with other planets during the turbulent early stages of the system's formation. Or it might be the result of a gravitational shove from a nearby, passing star that tugged the orbit into a vertical path. Alternatively, it could be the influence of a warp or a significant perturbation in the early protoplanetary disk itself, where the planet first formed, inheriting a skewed orientation. For any potential inhabitants, if such a world were to foster life, the seasons would be profoundly strange and unpredictable. The star might rise far to the north for decades, or even centuries, then slowly drift to the southern horizon as the planet continues its tilted, majestic path. Climate zones could migrate across the surface in incredibly long cycles, shaping evolution and geography in utterly unique ways, forcing any life to adapt to radical environmental shifts. These skewed orbits are like cosmic scars, clues to forgotten upheavals in a solar system's early history, offering a rare glimpse into the chaotic ballad that shaped worlds long before they found their present, peculiar paths. They demonstrate that the universe is not always neat and orderly. Sometimes, its most beautiful creations arise from a turbulent and violent past. Some solar systems have planets with highly eccentric orbits, while our Earth moves in a path that is nearly circular, a gentle, predictable ellipse around the Sun. Many exoplanets travel on highly stretched, elongated tracks. These eccentric orbits carry them from blistering proximity to their star, where they are seared by intense radiation, out into the frozen darkness of the system's outer reaches. These extreme orbital paths can be caused by powerful gravitational encounters with other massive planets within the system, by close stellar flybys from passing stars, or by leftover turbulence and gravitational instabilities from the planet's formation in the early disk. The surface of such an eccentric planet would experience seasons far more extreme than anything known on Earth. For part of its orbit, it could be scorched by intense radiation, its atmosphere swelling with heat, generating colossal storms and violent winds. Later, as it retreats into the frigid dark, that same atmosphere might freeze and condense, perhaps even raining out as snow or ice, creating cycles of evaporation and frost that dramatically reshape the world every few centuries or millennia. These immense temperature swings can fracture rocks, churn oceans into chaotic maelstroms, and sculpt landscapes with unforgiving, relentless power. Eccentric planets defy the calm, rhythmic predictability we associate with orbital motion. They reveal that even the steady, comforting heartbeat of a year can be bent and twisted by gravity's invisible, powerful hand. They are a testament to the universe's capacity for creating dynamic and often brutal environments, where the very forces that bind worlds together can also subject them to cycles of extreme change. These worlds are not just unusual, they are living laboratories of orbital mechanics, demonstrating the profound and often dramatic consequences of gravitational interactions on planetary evolution. Planets can be torn apart by the gravity of their star. It's a sobering reminder of the immense power of stellar gravity. When a planet orbits too close to its parent star, the tidal forces exerted by the star can become so overwhelming that they exceed the strength of the planet's own internal gravity, the very force holding it together. Layers of rock and atmosphere begin to peel away, shredded and vaporized, forming ghostly streams of material that spiral inward toward the star, like cosmic breadcrumbs marking their final, doomed journey. Over immense spans of time, what was once a solid, coherent world may slowly dwindle, reducing to a mere remnant core, perhaps surrounded by swirling clouds of glowing dust and gas. Astronomers have actually detected such doomed planets by the distinctive trails they leave behind, or by the spectroscopic signatures of vaporized metals in the star's atmosphere. These shredded worlds may eventually become diffuse rings of debris, vast dust belts, or even provide the raw material to fuel the formation of future planets in the same system, a grim form of cosmic recycling. This process of planetary unraveling is not quick. It may take millions of years for a planet to fully surrender and be torn apart under the relentless, crushing pull of its sun. Yet, the result is always the same, a powerful reminder that gravity giveth and gravity taketh away. It sculpts the fates of planets with the same quiet certainty that it ignites galaxies and molds stars. These unfortunate worlds are a stark illustration of the boundaries of planetary endurance, showing that even the most massive and seemingly robust planets can succumb to the overwhelming power of their parent star, becoming silent victims in the grand, ongoing dance of cosmic forces. Some solar systems contain asteroid belts far larger than our own. Our solar system features a prominent asteroid belt, a rocky debris field nestled between the orbits of Mars and Jupiter. But in the vastness of the cosmos, other systems feature belts that are hundreds, or even thousands of times more massive. These colossal belts are filled with an astonishing variety of objects, ranging from microscopic dust grains to mountain-sized fragments, and even larger planetesimals. These immense belts of debris may be the wreckage of worlds that never fully formed, their growth stalled by gravitational perturbations or a lack of sufficient material. Or, perhaps more dramatically, they could be the shattered remains of past collisions, colossal impacts that pulverized entire planets into countless pieces, leaving behind a vast field of cosmic rubble. The sheer volume of debris in such a system could fill the sky of any nearby planet with glittering shards and streaks of fire, especially if the system is still young and violent collisions are frequent, creating a spectacular, yet dangerous, celestial display. Such belts also serve as invaluable cosmic archives, preserving the chemical makeup of the original protoplanetary disk long after larger bodies have evolved. They can offer crucial clues about the initial conditions of the system, the types of materials available, and the processes that governed its early development. They may even play a vital role in seeding life on inner planets, delivering precious water and complex organic molecules during periods of heavy bombardment, acting as cosmic couriers of life's ingredients. These oversized rings of stone and ice reveal the unfinished business of planet-making, places where the leftovers of creation linger, participating in the cosmic story for aeons, slowly grinding down, colliding, and reshuffling, a constant, silent testament to the dynamic nature of solar system evolution. There are solar systems with 2 or more habitable zones. The concept of a habitable zone is typically imagined as a single, narrow band around a star where temperatures are just right for liquid water to exist on a planet's surface. However, in the rich tapestry of exoplanetary systems, there may be multiple such regions, expanding the canvas for potential life far beyond our initial assumptions. a star with a broad temperature range, perhaps one that experiences significant luminosity fluctuations, or a binary star system with two distinct sources of heat, can create overlapping or entirely distinct habitable bands. One region might comfortably support rocky planets with temperate conditions, much like Earth. Meanwhile, another, farther out in the system, could allow gas giants with large, watery moons to harbor life. Their oceans kept liquid by tidal heating and the reflected light of their parent planet. The idea of multiple habitable zones profoundly expands the canvas for potential biospheres, suggesting that life could arise in many more places than previously thought, each with its own unique set of environmental conditions. These habitable zones are not static. They shift and evolve over cosmic timescales as stars grow hotter or dimmer, or as binary companions change their orbital dance. This dynamic movement can create temporary windows of habitability, giving planets fleeting opportunities where conditions are just right for life to emerge and thrive. The presence of more than one such temperate band makes these systems exceptionally rich targets for future exploration, hinting at the extraordinary adaptability of nature when given the right conditions in more than one cosmic neighborhood. They are a powerful reminder that the universe's capacity to foster life is far more diverse and intricate than our single habitable zone perspective might initially suggest. The habitable zone can move as a star grows older. Stars, like all things in the universe, are not static. They undergo profound changes over billions of years, growing brighter and hotter as they steadily burn through their nuclear fuel. This stellar evolution, a slow, majestic process, causes the region around the star where liquid water can exist, the habitable zone, to gradually drift outward. A planet that was once comfortably temperate, perhaps an Earth-like world, may slowly become too hot, its oceans boiling away under increasing stellar radiation. Conversely, a frozen world farther out, once locked in an icy embrace, might thaw into a new Isis, its surface warming enough for liquid water to appear. Such planetary migrations through habitability can create epochs of life, separated by long ages of dormancy or extinction. Imagine life arising, flourishing, and then receding into a planetary deep sleep, waiting for the star's slow evolution to once again bring about favorable conditions. For a world like Earth, our own habitable window is temporary, slowly but inexorably edging toward a distant future where our oceans might boil and only the polar regions remain cool enough to sustain liquid water. These shifting habitable zones reveal that habitability is not a static, fixed condition, but a moving target, a dynamic dance shaped by stellar aging and planetary endurance. Understanding this intricate, long-term dynamic is crucial for scientists searching for life beyond our solar system. It helps them focus their efforts on planets that may only now be entering their golden age, even if they once lay far beyond the comforting reach of warmth and water. It also highlights the fragility and impermanence of life's tenure on any given world, emphasizing that even a seemingly stable environment is subject to the grand, slow changes dictated by stellar evolution. The universe, in its vastness, offers windows of opportunity, but they do not remain open forever. Some solar systems form in star-forming nebulas. In the brightest and most dynamic regions of the galaxy, vast nebulae glow with ionized gas and the brilliant light of newborn stars. These are the stellar nurseries, the cosmic wombs where solar systems are born in great numbers. Within these swirling clouds, filaments of gas and dust collapse under their own gravity, giving rise to clusters of stars, each of which then gathers its own disk of dust and ice. The environment within such a nebula is anything but serene. The intense radiation from nearby massive stars, which burn hot and fast, can profoundly sculpt these newborn planets, stripping away nascent atmospheres or igniting complex chemistry in ways impossible in quieter, more isolated neighborhoods. The sky of a planet forming in such a place would be a breathtaking, ever-changing spectacle. It would blaze with shifting clouds of red and blue, illuminated by the fierce ultraviolet glow of enormous, short-lived suns. Imagine a constant light show, a cosmic aurora writ large across the entire sky. Each world born in this turbulent environment carries the distinct imprint of its birthplace: rare metals from ancient supernovas, complex molecules from earlier generations of stars, and the lingering scars from radiation storms that battered its early, nascent surface. Nebula-born systems remind us that planetary creation is not always a gentle process. Sometimes it happens in the shadow of giants, under a sky that burns with the fire of 1,000 stars, a crucible of creation where worlds are forged in intense light and energy. These systems are laboratories of extreme planet formation, showing how matter can coalesce and survive even amidst the most energetic and dangerous regions of the galaxy. They are a testament to the resilience of the universe, capable of bringing forth new worlds even in the most dazzling and tumultuous of cosmic settings. Solar systems may begin forming even before a star is fully born. The story of a solar system often begins not with the star's first brilliant light, but in a subtle, quiet prelude. Even before a star's core ignites into steady nuclear fusion, while it is still gathering mass from the surrounding, collapsing cloud of gas and dust, its nascent gravity can already begin shaping a disk of swirling material. In these earliest, protostellar phases, tiny grains of dust collide and gently stick together, gradually forming pebbles, then boulders, and eventually the crucial seeds of planets known as planetesimals. Even as the proto-star flickers and contracts, slowly finding its form, these growing planetesimals are already carving lanes through the surrounding disk, accreting more material and casting the faint, subtle shadows of future worlds. In this twilight period, before the star settles into stable burning and truly becomes a luminous sun, the properties of the disk itself, its temperature, the magnetic turbulence within it, and the chemical gradients across its expanse, can predetermine what sort of planets will eventually form: rocky, icy, gaseous, or perhaps, in some cases, nothing at all. The solar system story, therefore, commences not with the star's first brilliant illumination, but with the quiet, intricate choreography of dust spirals and invisible gravitational forces. By the time the central star fully awakens and bursts into its long, stable life, its planetary children may already be well on their way to adulthood, having undergone significant growth and differentiation in the relative obscurity of their stellar parents' infancy. Observing these baby systems in real time is like watching a time-lapse film of our own solar system's youth, revealing not just what we are today, but what we were in the very earliest moments of cosmic creation. Every click of a telescope shutter catches a piece of that cosmic childhood, a fleeting glimpse into a history we can never physically relive. There are solar systems that are perfectly aligned and others that are chaotic. The universe, in its boundless creativity, presents us with a spectrum of planetary architectures. Some solar systems possess an almost serene symmetry, where all their planets orbit neatly in the same plane, gracefully aligned with the gentle, stately spin of their central star. These systems speak of a calm, undisturbed formation, a gentle accretion of material into a harmonious, flat disk. Others, however, are wild mosaics of tilted, twisted, and looping paths that profoundly defy the tidy logic seen in our own familiar neighborhood. In these chaotic systems, planets may orbit at sharp, often extreme, angles to one another, appearing to weave a tangled web of paths. Some might circle far above or below the star's equator, or even, in the most dramatic cases, orbit in a retrograde direction, moving against the star's rotation. These wild patterns often arise from ancient upheavals, giant impacts that radically altered a planet's tilt, powerful gravitational encounters with neighboring stars that perturbed entire systems, or turbulent collapses in the initial gas disk that never fully settled into a flat, orderly plane. The result of such a tumultuous past is a living snapshot of cosmic memory, an indelible imprint of every powerful force that shaped the system in its youth. By meticulously studying both the exquisitely orderly and the wildly unpredictable, astronomers learn that nature's blueprint for creating worlds allows for profound beauty not only in perfect balance, but also in glorious disorder. It proves that both harmony and chaos are fundamental parts of the cosmic design, each telling a unique story of formation, interaction, and evolution. These systems are silent, majestic archives of the universe's dynamic history, demonstrating that stability can be found in many forms, even amidst apparent disarray. Some planets never finish forming before their star burns away the material. Planetary formation is a delicate and often precarious race between growth and loss, and not all participants make it to the finish line. Around some young stars, the intense heat and powerful radiation unleashed during the star's ignition phase effectively burn away the last wisps of the protoplanetary disks. This happens before all the planetesimals, the small, solid building blocks, can fully assemble into mature, gravitationally rounded planets. These unfinished worlds can remain as massive, irregularly shaped asteroids, scattered rubble piles, or moon-sized bodies that are simply too small to round themselves into spheres or to hold onto stable, substantial atmospheres. Their surfaces often bear the stark, angular scars of countless collisions that were never followed by the gentle smoothing effect of sufficient gravity. Long after the gas and lighter dust have been dispersed into interstellar space, these fragments drift in silent, cold orbits. Poignant reminders of what might have been, if only time had stretched a bit further, or if the star had been a little less energetic. Studying these incomplete planets offers crucial insight into just how delicate the balance of timing and environmental conditions is in planet formation. It highlights the narrow window of opportunity during which a planet must accrete enough mass to become a fully formed world. Even the most promising beginnings can be cut short when a young star turns fierce too quickly, blowing away the very raw materials necessary for its offspring to grow. These quiet, unfulfilled systems are a testament to the many paths of cosmic evolution, showing that not every stellar nursery yields a complete and flourishing family of planets. They are the cosmic equivalent of unfinished sculptures, left behind when the sculptor's light grew too strong. We have detected solar systems forming around baby stars. The universe is a place of constant birth and renewal, and nowhere is this more evident than in the observation of solar systems actively forming around baby stars, also known as protostars. These nascent stars glow faintly, still gathering mass from the surrounding cloud of gas and dust, slowly evolving toward the stable, long-lived phase of a main sequence star. Around them, disks of dust and gas whirl in thick, luminous bands, gently warmed by the growing star's soft, nascent energy. Within these warm, churning disks, astronomers have detected the distinctive gaps and rings that are the telltale signs of the early stages of planet formation. These are the gravitational footprints of unseen, accumulating planets, already clearing paths in the dusty material. Planets in these systems might still be molten, their interiors churning with residual heat from their formation. They could be layered with hot ices, or still wrapped in thick, nebular atmospheres of hydrogen and helium slowly contracting. The entire system is a moving portrait of creation, a dynamic tableau of cosmic genesis. Dust grains spiral inward, ice giants carve glowing trails through the nebular material, and gas knots into the futures of weather, oceans, and skies. Observing these baby systems in real time is like watching a time lapse video of our own solar system's youth, a rare and invaluable glimpse into the very processes that shaped our home. It reveals not just what we are today, but what we were billions of years ago. Every click of a telescope shutter, every photon gathered from these distant, nascent worlds, captures a piece of that cosmic childhood we can never relive, providing profound insights into the universal mechanisms of planetary birth. These systems are truly living laboratories, showcasing the raw, energetic beauty of creation as it unfolds across the vastness of space. Some solar systems show signs of full planetary destruction. In some star systems, astronomers have uncovered overwhelming and often heartbreaking evidence that planets once existed, but no longer do. The most obvious clues are glowing rings of metallic dust orbiting the star, often found around white dwarfs. These remnants of stellar death are sometimes polluted with unusual abundances of silicon and iron, elements that should have sunk into the star's core, but instead linger in its thin surface layers, a cosmic fingerprint of a consumed world. Other signs include clouds of vaporized rock orbiting perilously close to the star, material that could only have come from a shattered planet. These are the scattered remains of worlds ripped apart by immense tidal forces, obliterated in the violent expansion of a dying star, or shattered by catastrophic collisions with other bodies. Even moons or minuscule pebbles may still be present, silently tracing the outlines of what once was a thriving system of worlds. Planetary destruction on such a scale serves as a stark reminder that solar systems are fragile, temporary arrangements. Their stories include not just birth and long, stable evolution, but also decay, violent erasure, and ultimate demise. And yet, even in destruction, there is a subtle form of contribution. The scattered material from these vanished worlds may one day contribute to the formation of new planets, reincarnating their atoms in the next generation of stars. These haunting systems are a poignant testament to the cyclical nature of the cosmos, where even the most devastating endings are merely a prelude to new beginnings. They are silent memorials to worlds that once were now reduced to dust and gas, but carrying within them the potential for future creation. Some solar systems can form in the galactic core. The very heart of a galaxy is not an empty void, but a region densely packed with stars, vast clouds of gas and dust, and immense, often chaotic, gravitational forces. Amidst this cosmic maelstrom, solar systems can indeed form. Though their environments are dramatically different from our relatively quiet, suburban region of the galaxy, stars born in the galactic core may be subjected to constant bombardment by radiation from nearby supernovas, or jostled by the powerful gravitational tides of incessantly passing stellar neighbors. Protoplanetary disks forming around these young stars would be incredibly rich in heavy elements, forged by previous generations of massive stars that lived and died rapidly in the galactic center. This abundance of heavy elements could allow planets to form quickly and often with a high metallic composition, creating worlds with super, dense cores. These planets, if they manage to survive the intense gravitational disturbances long enough, might develop unusual atmospheres, or highly compressed cores, constantly shaped by frequent close encounters. Life, if it were to arise in such a place, would have to adjust to a sky filled not with isolated pinpricks of light, but with an almost solid wall of nearby suns, a perpetual, blinding brilliance. The sheer density of stars would create a sky unlike anything we know, a dazzling, overwhelming spectacle of light. Solar systems at the galactic core remind us that planet formation is possible everywhere, even in the busiest, noisiest, and most energetic corners of the cosmic city. They challenge our assumptions about the conditions necessary for planetary birth, showing that the universe is capable of bringing forth worlds even in the most extreme and dynamic environments. Some planets have atmospheres made entirely of metal vapors, Imagine an atmosphere not of oxygen and nitrogen, nor even of hydrogen and helium, but of shimmering, gaseous metals. On certain ultra-hot exoplanets, those orbiting incredibly close to their parent stars, temperatures are so extreme that metals like sodium, magnesium, and even iron vaporize into gases. These metallic atmospheres would shimmer like liquid mirrors, reflecting and refracting starlight into brilliant, intricate spectral lines that our telescope instruments can detect from light years away. Winds on such worlds might flow at thousands of kilometers per hour, carrying streams of metal vapor from the perpetually irradiated day side to the cooler night side. On the night side, these metallic gases could condense into glittering clouds, or even rain down as molten droplets of iron or other heavy elements, creating a truly alien form of precipitation. The skies here are alien in every sense, with lightning storms potentially crackling through metallic haze, and no breath of oxygen or nitrogen to soften the air. The chemical reactions occurring in such an environment would be unique, driven by extreme temperatures and the constant cycling of vaporized metals. These shimmering worlds push the very definition of an atmosphere to its extremes, reminding us that what seems utterly unimaginable on Earth may be an entirely ordinary occurrence elsewhere in the cosmos. In space, even the air itself can be forged from fire and metal, creating environments that are both beautiful and terrifying in their uniqueness. They are silent, glowing testaments to the incredible diversity of planetary forms and compositions that the universe can create, pushing the boundaries of our terrestrial imagination. We have found planets that may rain glass or rubies. Imagine a sky that produces not water, but precious gemstones. Some planets possess atmospheres incredibly rich in exotic silicates and mineral compounds that, under specific conditions of temperature and pressure, condense into crystals rather than liquid water. On these worlds, colossal winds, driven by intense heat and planetary rotation, can hurl molten particles high into the air. As these particles cool rapidly in the upper atmosphere, they solidify into shimmering grains of glass, or perhaps even into precious gemstones like corundum, the very mineral behind sapphire and ruby. As gravity inevitably takes hold, these crystals fall like a colorful, glittering rain, scarring the surface or bouncing across vast, roiling oceans of liquid metals, creating a truly spectacular, yet abrasive, landscape. The combination of fierce, supersonic winds, extreme temperatures, and unique atmospheric chemistry creates landscapes that sparkle not with frost or dew, but with shining treasure torn directly from the sky. On such planets, storms can become legends, transforming the weather itself into a weapon of erosion or a wonder of unparalleled beauty. These places remind us that beauty, value, and danger often walk hand in hand in the cosmos. They demonstrate that the elements we know on Earth can be transformed into art and geology far beyond our wildest earthly imagination. These planets are not just scientifically intriguing, they are poetically beautiful, each crystalline drop a testament to the universe's capacity for creating dazzling and utterly alien phenomena, where the very air can give birth to jewels. Some solar systems contain planets that are tidally locked. Tidal locking is a common and fascinating phenomenon that occurs when a planet's rotation slows over time to precisely match its orbital period around its star. This leaves one side of the planet forever facing the star, bathed in perpetual daylight, while the other side is plunged into constant, unending night. This phenomenon is particularly common among worlds orbiting very close to dim, cool stars such as red dwarfs, where gravitational tides act quickly and powerfully. The daytime hemisphere of a tidally locked planet bakes under unending starlight, reaching scorching temperatures. Meanwhile, the night hemisphere chills to near absolute zero, a frigid realm of eternal darkness. This creates a planet profoundly cut in two by a stark, unyielding shadow line. In the twilight band, or terminator zone, between these two extremes, strange and often violent weather patterns swirl. Here, winds would constantly transport heat and gases from the day side to the night side in endless, powerful convection loops, attempting to equalize the extreme temperature difference. Oceans, if they exist, might cluster along this terminator zone, where conditions are more temperate, creating a narrow band of liquid water that could potentially harbor life. Life, if it were to exist, would adapt to a sky where the star never rises or sets, remaining fixed in one position, a perpetual beacon in the sky. While tidal locking challenges our traditional picture of habitability, recent models show that with the right kind of atmosphere or a sufficiently deep ocean, such planets could potentially support stable climates and even thriving ecosystems. Not all tidally locked worlds are lifeless. Some simply bear climates shaped by the relentless starlight on one side and the eternal night on the other, creating unique and enduring forms of planetary existence. Some planets spin so fast they almost break apart. The universe is full of extremes, and some exoplanets push the boundaries of rotation to astonishing limits. A few of these worlds spin so incredibly rapidly that their equators bulge outward dramatically, stretched by immense centrifugal force to the very brink of instability. These planets may complete a full rotation in just a few hours, whipping their atmospheres into colossal cyclones and flattening their overall shapes into oblate spheroids, resembling a cosmic M&M rather than a perfect sphere. At these dizzying speeds, gravity pulls harder at the poles than at the equator, creating wild differences in atmospheric pressure and temperature across the planet's surface. This can generate fierce firestorms, supersonic shock fronts, and extreme auroras, painting their skies in ways we cannot easily imagine, a constant display of atmospheric chaos and energy. If they spun any faster, the centrifugal force would overcome their own gravity, causing them to fling material into space or even tear apart entirely, disintegrating into a ring of debris. Their dizzying rotation is a crucial clue to their youth or their violent past. Perhaps it's a legacy of colossal collisions that imparted immense angular momentum, or a consequence of rapid inward migration that left them spinning like cosmic tops. These worlds are powerful testaments to the boundaries of planetary endurance, places where physics writes poetry at the very edge of destruction, showcasing the incredible forces that can shape and stress a celestial body to its absolute limits. They are a vivid reminder that stability, even for a planet, is a fragile balance of forces. Some planets reflect so much light they shine like mirrors. Far from our familiar skies, a handful of distant worlds shimmer with an extraordinary brilliance, like polished metal, returning an astonishing fraction of the starlight that falls upon them. Their extreme reflectivity, or albedo, can come from several remarkable sources. It might be due to incredibly bright cloud decks, seeded with tiny, highly reflective crystals, or perhaps from vaporized minerals that condense into reflective hazes in their upper atmospheres, or even from surfaces glazed into glass by relentless heat, creating vast, mirror-like plains. This high reflectivity transforms them into cosmic beacons, their brightness rising and falling as clouds migrate and colossal storms breathe across their perpetually day-lit sides. This flicker is a precious gift to astronomers, as these subtle changes in glow reveal crucial information about wind speeds, cloud heights, and even hints of atmospheric chemistry, all without the need for a single drop of landfall. Some of these gleaming planets circle so close to their suns that the mirror itself is a living, dynamic thing, constantly remade as minerals boil, travel on supersonic winds, and then settle again as glittering frost on the cooler parts of the atmosphere. Others are cooler, but mantled in vast sheets of ice or salts that keep them incredibly luminous, reflecting the faint starlight back into space. Each one is a natural signal flare, a luminous testament that tells us what its sky is made of and how its atmosphere interacts with the intense light of its star. They are beautiful, ethereal wonders, silent, shining mirrors in the cosmic dark, reflecting not just light, but the profound diversity of planetary surfaces and atmospheres across the universe. We have found planets that float in almost total darkness. Imagine worlds that travel through the vast, silent expanse of space without the comforting embrace of a parent sun. These are rogue planets, set adrift during turbulent youth, or perhaps never bound to a star in the first place, true cosmic wanderers. Without nearby starlight, their landscapes are lit only by the faint, residual red warmth of their own interior heat, slowly radiating into the void. Any atmosphere they might possess would become a slow, insulating blanket, desperately holding on to what little energy remains, while their surfaces freeze into vast, dark plains of ice. Where internal pressure grows immense, buried oceans may survive beneath thick shells of frozen gases, kept liquid by the steady, quiet murmur of radioactive warmth deep within their rocky cores. These planets are nearly invisible to conventional detection methods, their profound darkness making them exceptionally elusive. Yet, they reveal themselves through brief, fleeting gravitational lensing events. When their massive gravity bends the light of a distant background star, it creates a temporary brightening, a momentary flicker that betrays their otherwise unseen presence, before they slip away into the dark once more. A few of these rogue worlds are massive or young enough to still be warm, glowing faintly in infrared light, like embers drifting in a black, cosmic sea. They are profound reminders that planet-making is often a messy, chaotic process, and that the galaxy is sprinkled with countless lonely worlds, carrying their nights with them, silently drifting through the eternal dark. These solitary planets challenge our anthropocentric view of what constitutes a world, showing that existence can flourish even without the warming embrace of a sun, adapting to the profound silence and cold of interstellar space. Some solar systems have planets made of exotic matter. Most planets we know, including all those in our own solar system, are composed of familiar mixtures of rock, ice, and gas. But theory allows for the existence of objects far stranger, far more exotic than anything we have yet directly observed. If a collapsing protostellar cloud carries an unusual chemical composition, or if matter is exposed to extreme pressure and temperature for long periods, it can settle into states that seldom appear elsewhere in the universe. Deep interiors of such planets might become crystalline carbon on a colossal scale, forming vast diamond mantles. Or, under crushing pressure, hydrogen might transform into a metallic state, behaving like a sea of electrons, capable of conducting electricity. Some theoretical scenarios even predict ultra-dense forms of matter, packing more mass into less volume than any ordinary planet could possibly sustain. These hypothetical bodies would be incredibly small, yet ferociously heavy, with gravitational fields so intense that their surfaces might swallow meteoroids without a trace, their very existence defying our intuitive understanding of planetary mass. They might form in regions seeded by ancient supernovas, which enriched the interstellar medium with unusual elements, or near-compact, massive stars where tidal forces and pressure drive matter into extreme states. While we have not yet directly visited such places, their immense gravitational pull and the subtle ways they affect nearby starlight hint at their existence. They suggest that nature's playbook for building planets is far broader and more imaginative than our local sample suggests, capable of creating worlds from exotic matter that pushes the very boundaries of physics. These planets are a testament to the universe's capacity for surprise, proving that even the most fundamental building blocks of matter can be rearranged into truly alien forms. we have detected signs of planets being consumed by their stars. It's a cosmic tragedy, a slow, inexorable embrace that ends in dissolution. A star, as it swells in old age, expanding into a red giant, can grow large enough to physically touch and engulf a nearby world. When that happens, the planet's outer layers of gas and rock begin to spiral inward, leaving telltale fingerprints in the star itself. Astronomers can detect sudden, unexplained enrichments of elements like lithium and iron in stellar atmospheres, patterns that do not arise from normal stellar cooking. These are the chemical signatures of a planet being slowly digested. Some stars also spin faster than expected for their age, as if a recent, massive meal added angular momentum to their rotation. Around white dwarfs, the dense embers left after a sun, like star expires, heavy elements appear in the thin stellar surface, even though they should naturally sink quickly into the core. The only plausible explanation is a steady drizzle of planet crumbs and asteroid dust, falling in from disrupted orbits, remnants of a vanished system. Infrared glows from hot debris rings and tiny, irregularly repeating dips in starlight complete this haunting picture of consumption. What we witness is not a single catastrophe, but a menu of endings, each showing how gravity, that fundamental force, eventually collects what it once allowed to wander. These observations are a poignant reminder of the ultimate fate of many solar systems, including our own distant future, where planets may eventually be reabsorbed by the very star that gave them life. They reveal that the universe is a place of constant transformation, where even worlds are not immune to the relentless, consuming power of their parent stars. Some planets have magnetic fields far stronger than Jupiter's. Giant planets, with their roaring, turbulent interiors, can generate immense magnetic fields that dwarf anything found in our solar system, making Jupiter's powerful magnetosphere seem modest by comparison. Fast rotation, combined with deep layers of highly conductive fluid. Perhaps metallic hydrogen under crushing pressure, or vast salty oceans wrapped around Earth cores, acts like a colossal dynamo. This process converts the planet's internal heat and motion into vast, invisible shields of magnetism. These incredibly strong fields trap charged particles from the stellar wind, funneling them into the planet's poles, where auroras bloom with such intensity that they can outshine the host star in radio light. The space around such a world becomes a veritable fortress of magnetism, with massive bow shocks forming where the stellar wind slams into the magnetosphere, and plasma tails stretching for millions of kilometers into space. The sheer strength of the field offers crucial clues about the constitution of the planet's interior, providing insights into its deep-seated geology and dynamics. When a planet with a powerful magnetosphere skims incredibly close to its star, magnetic interactions can become incredibly dynamic. These interactions can even heat the planet's upper atmosphere, altering the chemistry of its auroral glow and revealing the intricate interplay between stellar and planetary magnetic fields. By listening for those radio murmurings and watching for subtle ultraviolet flashes, astronomers learn to weigh the hearts of distant worlds, deciphering the secrets of their powerful, unseen shields. These planets are silent, invisible giants whose presence is only betrayed by the immense forces they unleash into the cosmos. There are solar systems with more than one asteroid belt. Our solar system has one well-known asteroid belt nestled between Mars and Jupiter. But beyond many other stars, astronomers have discovered not one, but several belts of leftover building blocks, stacked like nested rings, each a testament to a different stage of a system's formation. Each belt carries a distinct temperature and composition, warm inner debris fields rich in rocky fragments, and colder outer regions stocked with volatile ices and complex organic compounds. The gaps between these belts are not empty mistakes. They are often the subtle, yet unmistakable, signatures of unseen planets that have quietly swept lanes clear of debris or locked dust into intricate resonant patterns. The complex structure of these multiple belts reveals a rich history of growth and interruption, of worlds that formed quickly and others whose development stalled. Collisions within these belts constantly grind larger bodies down into fine dust, which shines brightly in infrared light, eloquently outlining the system's architecture like chalk on a blackboard. In young, highly active systems, that dust brightens and fades on human timescales as smash-ups come and go, providing a dynamic, real-time view of ongoing planet formation. In older systems, the remaining belts persist as cosmic archives, preserving a detailed record of the raw materials that once circled far more thickly, before being incorporated into planets or scattered into space. These multi-layered rings of stone and ice are a testament to the unfinished business of planet-making, where the leftovers of creation linger and continue to participate in the cosmic story for eons, slowly evolving and reshaping themselves. Some solar systems form around stars too small to be seen with the naked eye. The universe is teeming with stars that are far smaller and cooler than our sun, appearing as mere red embers on the cosmic stove. These are red dwarfs or brown dwarfs, and many of them quietly host their own planetary systems. Their protoplanetary disks are often smaller and longer, lived than those around brighter suns, which gives small worlds ample time to grow and accrete material, even if the process is slower. Planets in these systems often orbit snugly close to their tiny stars, receiving present levels of warmth despite the star's faintness. While the stellar light would appear dim and distinctly red to human eyes, providing a perpetual twilight rather than bright daylight, these conditions can still be conducive to life. Flares can be frequent in the star's youth, but over long spans, the steps toward stability arrive, and atmospheres that are dense or magnetically shielded can endure. Because these stars are incredibly faint and extraordinarily common, their planets make up a surprisingly large share of the potentially habitable real estate in the galaxy. Transits of these planets repeat often due to their tight orbits, which allows observers to meticulously map atmospheres, track seasonal changes, and sometimes even detect weather patterns. From a surface bathed in crimson noon, the parent star would loom large and steady, a constant, dim red sun. The possibilities that gather around these small, quiet fires are not small at all. They represent a vast, often overlooked, frontier in the search for life, proving that even a star that barely glows can shape an entire, thriving planetary family. We have observed planets that orbit inside stellar winds. Every active star, including our Sun, constantly breathes a river of charged particles, a stellar wind, that flows outward in all directions through its system. Some planets circle so incredibly near to that powerful breath that their very skies are carved and shaped by constant, intense particle storms. At the boundary where the stellar wind meets the planet's magnetic field, powerful shock fronts form, accelerating particles into brilliant auroras that can encircle entire hemispheres, glowing with an otherworldly light. The stellar wind relentlessly strips away lighter gases from the planet's atmosphere, sculpts plasma tails that stream millions of kilometers into space, and can even induce electric currents that heat the upper atmosphere from within. These environments are incredibly harsh, yet remarkably informative. The way a planet resists or yields to this constant bombardment tells us whether it possesses a global magnetic field, how dense its atmosphere might be, and what volatile elements are present in its upper layers. As the star cycles between quiet and active periods, its stellar wind changes in intensity, and the planet's atmospheric response changes rhythmically in turn. To watch such a world is to see a dynamic, ongoing process that begins at the heart of a sun and ends in a planetary sky, a complete circuit from stellar heartbeat to planetary glow. These planets are living laboratories of star-planet interaction, showcasing the profound and often destructive influence of stellar activity on the evolution and survival of planetary atmospheres. They are silent sentinels, enduring the ceaseless breath of their parent stars, their very existence a testament to the forces that shape cosmic environments. Some solar systems have planets with comet-like tails. Not all tails belong to comets, those icy wanderers of the outer solar system. Some close-in planets, orbiting perilously near their stars, shed gas so quickly and profusely that a long, ethereal stream trails behind them, curved by their orbital motion and pushed outward by the relentless pressure of starlight. This comet-like tail can be made of hydrogen, violently torn from an upper atmosphere, or even heavier vapors from rocks that evaporate under fierce, intense heat, creating a mesmerizing, glowing plume. When such a planet passes in front of its star, its tail begins blocking starlight long before the planet itself arrives, and continues to block light long after the planet has departed, creating a transit with a distinctive, drawn-out entrance and exit. Different colors of light are absorbed at different points along the stream, which allows observers to meticulously separate the chemical ingredients of the tail and watch how they change with time. These tails can break into clumps, fade, and then regrow as the stellar wind changes in intensity, creating a dynamic, ever-shifting spectacle. They are living records of atmospheric escape, showing how a world slowly loses its breath to its sun, and how quickly a fragile sky can thin and vanish into the vacuum of space. These planets, with their ghostly, trailing plumes, are a poignant reminder of the delicate balance that holds an atmosphere together, and the powerful, erosive forces that can strip it away, atom by atom. They are silent, luminous testaments to the continuous, subtle destruction and transformation that unfolds across the vast, dynamic canvas of the universe. We have found planets that orbit black holes. Worlds can indeed circle the darkest, most enigmatic objects in the cosmos, black holes. These planets are bound not by the warmth and light of a star, but solely by the immense, unwavering power of gravity itself. In such a system, daylight would come from a distant companion star, if one exists, or from the eerie, glowing disk of gas and dust spiraling toward the black hole's event horizon, known as an accretion disk. The orbits of such planets must be wide enough to avoid the destructive tidal forces that would tear them apart, yet close enough to remain gravitationally bound against the tug of passing stars. Detecting these elusive worlds is incredibly difficult, so the evidence arrives in subtle, piecemeal clues. Subtle gravitational lensing events, where the black hole's mass bends distant starlight, might hint that a compact, massive center carries a lighter companion. Flickers in the light of accretion disks might suggest an unseen planet shepherding gas into waves, like a shepherd dog guiding a flock. The physics in such an environment is stark, yet surprisingly, not entirely hostile to stability. If conditions are calm, and radiation levels from the accretion disk are modest, moons and atmospheres could potentially persist for very long periods, sustained by internal heat or the faint glow of the accretion disk. In these remote, extreme pressings of the cosmos, the ultimate ruler is gravity itself, and a planet survives by learning the quiet, precise geometry of a deep well in spacetime. These black hole, orbiting worlds are a testament to the universe's boundless capacity for creating stable structures in the most unexpected and extreme environments, pushing the very boundaries of what we conceive a solar system to be. Some planets never experience night at all. On certain worlds, the very concept of night, that familiar rhythm of darkness and rest, simply does not exist. These planets either rotate so incredibly slowly that one side is perpetually illuminated for aeons, or they are tidally locked to their stars, resulting in one hemisphere bathed in perpetual daylight, while the other is frozen in endless, unyielding shadow. On the day side, the sun never sets, climbing only slightly across the sky as years and centuries pass, blazing down with unbroken, relentless radiation. Temperatures on these perpetual day sides climb to extraordinary levels, creating atmospheres filled with towering clouds of steam or dust, and winds that swirl constantly in massive convection loops. Vegetation or life, if it ever evolves on such a world, would have to grow without rest, adapting to blinding, relentless light and extreme heat. The twilight zone, a narrow band between the two extremes, might hold the only refuge. A thin strip where the scorching heat of the day and the frigid cold of the night find a fleeting, precarious balance. This terminator zone could be a dynamic, constantly shifting region with unique weather patterns and ecological niches. These worlds show that a planet's rhythm, its fundamental breathing in and out of light and shadow, is not a universal constant. Some planets live in eternal day, never knowing the calm, cooling embrace of darkness, their ecosystems shaped by an unending stellar glare. They challenge our deeply ingrained assumptions about the fundamental cycles of a day, revealing the vast diversity of planetary experiences across the universe. They are a powerful reminder that life, if it exists, can adapt to an astonishing array of environmental extremes, even to the absence of night itself. There are solar systems with planets that glow from their own heat. Imagine worlds that are not merely illuminated by their stars, but that radiate so intensely with internal heat that they actually shine faintly in infrared or even visible light. These glowing worlds may still be cooling from their violent birth, their interiors churning with molten rock and compressed metals, radiating the residual energy of their formation into space. Others generate immense heat through relentless tidal friction, pulled and squeezed by the immense gravity of nearby giants in a perpetual, internal cycle of flexing and release, much like a constantly kneaded ball of dough. Their internal energy oozes outward, creating surfaces that may shimmer with vast molten lakes, glowing clouds of superheated vapor, or burning atmospheres rich in vaporized elements, casting an eerie, self-generated light. From afar, these planets might appear like miniature, dim stars, quietly orbiting larger ones, their warmth creating soft, luminous halos in telescope images. In time, they may cool, darken, and settle into a more familiar silence, their internal fires gradually diminishing. But for millions of years, they blaze with the fierce, primordial fire of youth, a testament to the immense energy locked within their interiors. Their self-generated heat is a powerful reminder that planets are not merely dark, passive rocks circling luminous suns. Sometimes, they are suns in miniature, carrying their own inner flame, their own source of light and warmth. These glowing worlds offer a glimpse into the dynamic, energetic processes that shape planetary evolution, showcasing the incredible range of thermal states a celestial body can experience, from the frigid cold of deep space to the luminous glow of a newborn world. We have detected solar systems that are still swirling with dust. Many solar systems never completely clear the chaos and lingering remnants of their childhood. Long after planets have formed and settled into their orbits, the space between them can remain filled with vast, ethereal clouds of microscopic dust grains, shattered fragments of comets, and pulverized rock. These lingering debris fields reflect starlight in a glowing haze, a subtle, shimmering veil that permeates the system.